So hello everyone. We have discussed so far various topics about memory and memory hierarchy. Now it's time to talk about the input and output devices and how they are handled in computers, particularly communication protocols, technology devices out there to help CPUs communicate with other computer peripherals. It's important to understand the relationship between a CPU and an I/O device because without these devices, computers won't be interesting and powerful. There might be various devices that can be connected to a CPU. These devices can be keyboards, mouse, and secondary storage devices such as hard disk drives and liquid crystal displays for graphics, right? Depending on the operation, the build technology, and manufacturing, these peripherals can exhibit different data rates, and each might have different maximums. Therefore, the bus system must be designed to handle the highest transfer rates between peripherals and memory. Peripherals are often electromechanical devices, and therefore a conversion of signal values may be required. Due to different speeds, synchronization may also be needed. In addition, format is usually different for each device. To resolve all these issues, computer systems include special hardware to supervise and synchronize all input and output transfers. These components are called interface units or controllers or drivers depending on the context. And here is the table to show you how diverse are the I/O devices are in today's world when you compare them in terms of data rates. Each has different requirements in response time and throughput, and interesting of all is that CPU must promptly be responsive to all of these devices without hurting end user experience and maintain the efficient hardware utilization. So let's look at the structure of a typical system. The picture here shows a single CPU attached to the main memory of the system via some kind of memory bus or interconnect. Some devices are connected to the system via a general I/O bus, which in many modern systems would be PCI, or one of its many derivatives. Graphics and some other higher performance I/O devices or higher bandwidth required I/O devices might be found here. Finally, even lower down are one or more of what we call a peripheral bus, such as SCSI, SATA, or USB. These connect the slowest devices, to the system, including disks, mouse, and other similar components. As can be seen from the picture, we have a hierarchical structure. So why do we need a hierarchical structure like this? Simply put, physics and cost. For example, engineering a bus for high performance is quite costly, and slow devices are kind of stay away from CPU. In this hierarchy. A device has two major components, interface I/O unit and internals. Interface has status, command, and data registers. Status register can have values like busy or available so that the operating system will know the status of the device through some sort of polling. Operating system waits until the device is ready to receive a command by repeatedly reading the status register. We call this polling the device. The data register holds the data to be processed, and it's usually loaded before the command so that the data will be ready by the time the command is loaded into the command register. By reading and writing these registers, the operating system can control device behavior. On the other hand, all the internal structure is responsible for implementing the abstraction the device presents to the system. Some of the devices may include a simple CPU, some general purpose memory, and other device-specific chips to get the job done. Data transfer between the central computer and the I/O device may be handled in a variety of modes, some of which we use the CPU as an intermediate path, while the others transfer the data directly to and from the memory. Data transfer to and from peripherals may be handled in one of the three possible modes. The first mode is programmed I/O, which basically consists of operations, and these are the result of I/O instructions written inside the computer program. For example, x86 has in and out instructions for this purpose. Transferring data under program control requires constant polling for the status of the peripheral being available. However, this will keep CPU busy needlessly in case the peripheral is busy with I/O task. This can be avoided by using the interrupt facility, and which is the second mode of transfer, interrupt initiated I/O. So the CPU raises a request, puts the request on hold or sleep, and context switch to another process. When the I/O is finished and device gets done with the job, it raises a hardware interrupt so that the CPU jumps into operating system interrupt handler, and that piece of code finishes the job and wakes the waiting processes up and give the requested data back. Such transfer is called interrupt initiated I/O, as we said, and is used for keyboard controllers. And finally, we have got the direct memory access, which will be covered in the next slide. Although interrupts allow for overlap of computation and I/O, they only really make sense for slow devices. Otherwise, the cost of interrupt handling and context switching may outweigh the benefits interrupts provide. There are also cases where a flood of interrupts may overflow a system and lead it to live lock. In such cases, polling provides more control to the operating system in its scheduling and therefore is again useful. If the speed of the device is not known, or sometimes fast and sometimes slow, it may be best to use a hybrid approach that polls for a little while, and then, if the device is not yet finished, uses interrupts. This two-phased approach may achieve the best of both worlds. Another issue is when using programmed I/O, to transfer a large chunk of data to a device, the CPU is once again overburdened with a rather trivial task, and therefore wastes a lot of time and effort that could better be spent running other processes. A DMA, direct memory access engine, is usually a very specific device within a system that can orchestrate transfers between devices and main memory without much CPU intervention. So DMA works as follows. To transfer data to the device, for example, the operating system would program the DMA engine and communicate with it through CPU by telling it where the data lives in memory, how much data to copy, and which device to send it to. At the CPU level, there are also control signals such as bits for read, write, and start DMA signals. At that point, the operating system and CPU is done with the transfer and can proceed with other work. I/O device and the peripheral is directly connected through data bus, and the transfer is managed by the DMA. When the DMA uses the memory bus, CPU is temporarily disabled to access that bus. As the data moves from peripheral to memory or vice versa, the word count decrements and the address register increments to point to the next memory location to continue transfer. When the count hits 0, it means the DMA is complete transferring. The DMA controller raises an interrupt, and the operating system therefore knows the transfer is complete and switches back to the old process and continues its execution. Finally, note about DMA is that many computers combine the device interface logic with DMA into one unit called I/O processor. In such a system, a computer is divided into 3 separate modules: the memory unit, the CPU, and the I/O processor. I/O processor also handles multiple devices and multiple I/O operations without CPU interference. There are 2 primary methods of device communication. The first option is to generate explicit I/O instructions, also known as port-mapped I/O. These instructions specify a way for the operating system to send data to specific device register and therefore allow the construction of the protocols. To send data to a device, the caller specifies a register with the data in it and a specific port which names the device. Executing the instruction leads to the desired I/O behavior. These instructions are usually privileged to prevent access to peripheral devices randomly and used by the operating system kernel. The second method to interact with these devices is known as memory mapped I/O. With this approach, the hardware makes device registers available as if they were memory locations. To access a particular register, the operating system issues a load to read or store to write the address. The hardware then routes the load store instructions to the device instead of main memory through using the same bus. To accommodate the I/O devices, areas of the addresses used by the CPU must be reserved for the I/O and must not be available for normal physical memory or user. There is no single winner among these two approaches, and both types of interactions are used in today's world. There is always a possibility that several resources will request service simultaneously. In that case, the system must decide which device to service first. A priority interrupt mechanism establishes a priority routine among various interrupt sources. Devices with high-speed transfers are given precedence over the rest of the devices, for example. Hard drives, data rates are higher than keyboard data rates, and therefore they are given priority when handling or processing interrupts. In the software interrupt, the program jumps to a common polling service to identify the interrupt source of highest priority. After finding the most prioritized interrupt request, the program is branching to the highest priority service routine. The disadvantage of software priority interrupts is the time required to poll all the devices, and that this may well exceed the time permitted to perform the actual I/O operation. Alternative way is the hardware interrupts. One of the most popular ones is the daisy chain model, as shown in this slide. In this method, the device with the highest priority, is placed first position, and it's followed by other devices with descending order in priority. When the interrupts are requested, CPU sends an interrupt acknowledgement to the highest priority device. If this device did not originate the request, it goes to the next device, etc., and etc. Hardware priority interrupt mechanism is a very fast option in handling multiple interrupts in a computer system. Let us look at the communication technologies that enable data address and control signals being transferred over buses and computer system. As for the I/O transmission, the serial communication is used, and serial communication might seem like a slower option compared to parallel communication, but it has got its own advantages, such as it creates less skew in the clock, and it's easier to synchronize and less costly to build. The signals are usually digital, and inputs might be in analog form. In that case, an analog to digital conversion must be done through what's called modems. There are three modes of communication: simplex, half-duplex, and full-duplex. Simplex is a single-direction communication, so the receiver need not to send anything back in case of any transmission. And TV broadcast scenario is a great example to that. Second is a half-duplex mode, and it goes with both directions but one direction at a time. And finally, full-duplex mode allows simultaneous communications at both directions. There are two types of communications: it's synchronous or it's asynchronous. Synchronous communication uses the same clock and it needs to be synced, so sometimes synchronization information needs to be sent for this purpose, and it's sent along with the data to the destination. Asynchronous communication, on the other hand, sends information whenever it's available. So channel can stay idle for long periods of time. If not, there is nothing to send. So as you can observe that the channel might not be very well utilized in that case. When you press, so in this case, I want to talk about a great example of a keyboard, which is, I think, the indispensable part of a computer system. So keyboard has buttons on it. So I'm going to talk about when you press a button, what happens. What happens is that it gets translated into a K-scan code, which is then synchronously transmitted to the keyboard controller in the computer. The microcontroller in the keyboard controller puts the scan code into one of the input or output registers for CPU to come and read. Along with this operation, an interrupt is also sent. A hardware interrupt handling routine reads the scan code and puts it in a reserved memory area, where the BIOS, or we call Basic Input Output System, can translate that scan code to ASCII character code for use by different applications. Similarly, output register can be used to control the keyboard actions. Status register, on the other hand, reports specific information on the status of the keyboard. For example, busy, available, some things like that. And also the keyboard controller has that status register as well. As you can see, it's interesting to observe that there are three working engines to complete the accurate operation of a keyboard. Issuing a read or write request to different types of drives, it's a very very, very complicated process. Think of SCSI or ID device or USB devices. All have their own interfaces, and they are working according to different formats, some predetermined format. The main objective of a designer or an operating system writer is to keep most of the operating system and devices, interaction neutral, and provide a generic interface. The solution is actually embedded in the lowest level. A piece of software in the operating system which must know in detail how a device works. We call this piece of software a device driver. Any specific device interaction are encapsulated within that device with driver. Interestingly, because device drivers are needed for any device you might plug into your system, over time they have become to represent a huge percentage of the kernel code. Studies show that 70% of the operating system code is found in device drivers. Therefore, when people talk about operating system having millions of lines of code, what they're really trying to say is the operating system has millions of lines of code of device driver code. Of course, for any given installation, most of that code might not be active. Anyways, it's just a piece of information for you to keep in the back of your mind. So in this class, we intended to cover basic I/O concepts as well as some of the trade-offs regarding the I/O subsystem integration into a computing machine. We also have touched upon some of the concepts from the operating system point of view, such as device drivers and keyboard interactions. We will have few in-class exercises to complement what we have discussed and learned in this video. In the next lecture, we'll hopefully remember microarchitecture concepts again and build on it some new ideas for improved CPU performance. And these new ideas include, but not limited to, pipelining. So please stay tuned and feel free to drop any questions you might have about today's lecture, and I'll be more than happy to help you. And thank you very much. See you next time.